think mostly ODINN, which is a project, a library, a large-scale glacier model that we've been developing the last 3 years. It's pretty much work in progress compared to very solid results I've seen so far. And I will mostly be focusing on two aspects of the use of Julia. First of all, multi-language interoperability, and also how to leverage the SciML ecosystem for geoscientific modeling. So first of all, when I mean a glacier model, what is it? So as you can see in this animation, there's a lot of things going on glaciers. First of all, from my opinion, they are one of the coolest systems on Earth. And in order to simulate them, first of all, we need observations. So we have two main types of observations. The first one is field work. We go to the glacier and we normally have point observations, high quality data, but super sparse. And the other main type of observation is satellite remote sensing. So in the recent decades, there's a huge increase in satellite remote sensing, and they have a very good spatial coverage. And it's this that is mostly revolutionizing a bit the way we can model glaciers. But then, of course, in terms of modeling, we need to model two main things. So the first thing is ice and atmosphere interactions, and then ice-ocean interactions. So this mainly determines the gain or loss of mass of the system. And the second one, which is pretty evident from this animation, is the ice flow dynamics. So basically, as a bit like Mauro said, how the ice deforms or slides at its bed. But then, in this context, so and also in the wider context of geoscientific modeling, why is Julia so interesting? So as I show you here, we always have these two ingredients, data and then some models. So these two elements for geoscientific model have very specific characteristics. On the one hand, data is always spatiotemporal, highly sparse, and very noisy. And this is both the case from satellite remote sensing and in situ data. And then in terms of models, these models, they need to work at different spatiotemporal scales. We need to simulate maybe 1 day to multiple centuries. And sometimes if we have to work at the scale of the globe and then resolve something as small as maybe cloud microphysics, we will not explicitly resolve those, so we'll use empirical parameterizations. And then importantly, since on Earth everything is connected, we need models that can be easily coupled among them, especially, for example, to simulate the interactions between the ocean and the atmosphere. So why is Julia so interesting here? Because from my point of view, two main ingredients. The first one is differentiable programming. If we can compute the gradients of our model, then we can easily assimilate and digest all of those huge amounts of data, and then we can perform very cool inversions or optimizations. And the second ingredient is this multi-language interoperability, because as we have seen here, we really need to couple these models between them. And unfortunately, not all models are coded in Julia, so we need to talk to the outer world, and Julia is very good at this. So what is ODINN? So in a nutshell, basically, we're building a scientific machine learning glacier model. And we're building a modeling framework which intends, of course, to assimilate all these heterogeneous Earth data for glaciers coming from satellite remote sensing, in situ data, and also climate models. And the idea is, of course, to use these differentiable programming capabilities to assimilate these observations in the modeling framework. And we have one main scientific objective in mind, which is to discover new laws. And by laws, I mean mostly parameterizations and empirical laws. And the thing that we're really heavily trying to investigate here is the use of universal differential equations. And by this, I mean basically to use partial differential equations to solve them with traditional numerical solvers and to embed a regressor, for example, a neural network, to parameterize a subpart of that equation, normally to capture some missing physics or just to explore some unresolved processes. So the main goal here is basically to parameterize key physical processes of glaciers, with the goal, of course, to improve these models and then to perform glacier evolution predictions under different scenarios of climate change in order to understand how they will evolve in the future. This modeling framework is purely coded in Julia, but an important piece here is that we heavily rely on two Python packages, and for this we rely on PyCall. And these two packages are, first of all, the Open Global Glacier Model, which is a very big community-based model in Python, which we purely use to retrieve the initial conditions, so all the topographical and the climate data for our glaciers. And then we use Xarray to process and all these large data sets. So just a quick overview of ODINN. This is a publication that we published last year where we presented a synthetic study to understand the properties of UDEs with this type of partial differential equations. So we use this Python package to retrieve all the initial conditions of our glacier, and then we build a universal differential equation using the SciML ecosystem. We have this partial differential equation describing the flow of ice, and then we embed a neural network in it, like describing a physical law. For example, here it was the changes in the viscosity of the ice. And then we run this forward with a numerical solver until we hit some observations. We compute an error in the loss, and then we use this to optimize the parameters of the neural network like iteratively until we fit the observations. So if you want like the details, you can check the QR code there. So these 3 years were not a walk in the park. So we learned a lot of lessons, some good and some like harder. The first takeaway for me would be like that UDEs right now, for small problems, they work pretty well. Like by small problems, I mean like simple code architectures and a reduced number of ODEs. So this, we can already tackle very cool like research questions with that. But with the type of big problems that we're tackling here, it's still pretty rough, and mostly because of the common thread that everyone is mentioning, enzyme. We need good AD support for these big problems. It's coming, but it's still not there. So from this standpoint, what are the perspectives on where we're going? So first of all, we're working towards a 1.0 release, and by 1.0, I don't mean like as mature as maybe the previous models that we see. It's just like we completely refactored the architecture and the API, like splitting it in 4 packages, and we're also building towards compatibility with enzyme. And we're mainly developing the model with 2 objectives in mind. The first one is this, inferring parameterizations of these key processes of glaciers from these sparse observations of glaciers and any Earth observation that can be interesting here. And of course, the scientific aspect here is we want to assess the impact of glacier retreat under climate change on water resources in vulnerable regions such as the Andes or in high mountain Asia. So if this is of interest to you, first of all, please check out the GitHub repository. We welcome like more developers in the earth sciences aspects or in the SciML aspects. And also I would like to advertise that I have an open postdoc position for 2 years to work with me in Grenoble in the beautiful French Alps. So if you like SciML and earth sciences or glaciers, you will be able to visit them. They're here, and also work on them on Julia. And the second advertisement is like we recently released a review paper on arXiv on differentiable programming for differential equations. So if you like this topic, please check it out because Facu did an amazing job, and it's 50 pages long, so it covers a lot of the details. So with this, I thank you for your attention, and I'm happy to take questions.
Okay. Who has any questions? Can get to one here, okay.
I'm just curious what you mentioned your model is not compatible with automatic differentiation yet?
No, it is compatible. It's just that like in this paper that we published, we used like reverse diff, which worked well, but it's just because we had like a simple model architecture to make it work. And now we upscale it to like a bit like the same philosophy, modular with nested structs and so on. And when we moved to this more complex architecture, it completely broke. So now we are kind of like aiming to work with enzyme in order to have like this full compatibility with all these features.
Okay, but it's not just a scale question. It's actually something different in the model when you
I'm sorry?
I don't quite understand what is causing it not to be compatible with the automatic differentiation anymore.
I mean, it's not that it's not compatible with automatic differentiation. It's not compatible with some libraries. And I mean, there's many things that don't work with enzyme, but it's mostly like garbage collector and PyCall compatibility. Like Chris knows all the details.
Okay, thank you.
So last question, and then we go to the break. We are already kind of over time, but should be fine.
Yeah, well, I was just going to comment on what's going on with their AD issue, right? So the AD issue that they're having is mostly edge cases in the garbage collector because, for example, when you read in the glaciers, you end up reading them as Xarrays that are owned by Python, but then are worked on by enzyme. And so you need to make sure that the garbage collector from Enzyme knows how to deal with this interlanguage stuff and does not free things that live in another language. These are different, edge cases in the garbage collector that Enzyme had not handled before. And so we are working with Billy to make sure that we can, handle these cases. There's another case with timeroutputs.jl, which, because that uses a direct global reference and such. So it's nothing to do with the numerical codes at this point. Like the numerical stuff is all differentiating just fine. It's just like all this other, I use PyCall plus this, plus this, plus this, plus this, and I piece it together. These are the things that are now in the realm of making Enzyme mature and robust for those aspects.
Okay. So thank you, Jordi.